Finally, in the last part of this video, we see some simple approach to model crowds of character. When lots of characters are involved and viewed from far away, the simplest representation we can use for each of them is to be a single particle. Then an idea to give to these individual particles an impression of being animated and interacting as a group is to introduce some simple forces. A common method inspires from attraction and repulsion forces in physics and simply states that particles are attracted together at a certain distance to form a group. But when two particles come too close together, then they are repulsed at short range. And this very simple model was actually very successful to mimic the appearance of crowd, typically herds of animals. This model is called the Boyd's model and was introduced by Craig Reynolds in 1987. If you look at the Boyd's model, the particle is defined by a position, a speed, and the force acting on it. There was initially 3 basic forces took into account, expressing steering behaviors to model flocks of birds, for instance. The cohesion force, attracting particles together in a given neighborhood, the alignment of velocity direction between neighboring particles so that they have a tendency to move as a group in the same direction, and the separation force when particles are too close to each other. And using these simple forces leads to a global behavior that is said to be emerging, as if a global motion that looks complex was emerging from these very simple rules at the individual level. Here is an example of forces that you can apply to the particles. You can set initially some random particles with initial position and velocity, and you can compute the attraction and repulsion forces depending on their pairwise distances, the norm of pi minus pj. Different type of force profiles as a function of distance can be used. We can use the inverse of distances or exponential and Gaussian ones. These profiles need to be adjusted as they have a strong influence on the type of grouping and motion of the result. And once the forces are computed, then the velocity and position of the particles can be integrated along time numerically. Here is an example of algorithm we can follow to update the force in looping over all pairs of particles and summing their forces before applying the numerical integration. Of course, if we compute all pairwise forces like that, the algorithmic complexity will be of n squared, where n is the number of particles. And as we are aiming at having a lot of particles, it can quickly get slow to compute, while spending a lot of time on faraway particles that may have very limited interaction. So to improve the efficiency of the approach, standard spatial sorting algorithm can be used in order to pre-sort particles that are sufficiently close together to be in interaction, and we can use all types of acceleration structure from simple uniform grid to octrees when dealing with multiple groups that are far away. Despite its simplicity, the Boyd's model can provide very convincing results for flocks like birds and fishes. Of course, to improve the visual result, the particle can actually be displayed as a 3D animated model, and we can use skinning, for instance, to animate it as an articulated model. Other behavior can be added, like following an objective position, having specific target speed, avoiding constraints, or avoiding some type of particles, also to have a model of prey and predator. A famous example of usage of Boyd's in cinema is the use it in the movie Batman, where it was used to model the motion of the bats, as well as some of the penguins whose geometry were refined afterwards. The Boyd's model has, of course, some limitation. One thing we should avoid is the collision between the models, and actually the Boyd's doesn't prevent collision from happening. It can happen due to the numerical integration, and of course, if you use a geometrical model over the particle position, parts of them can collide together. Also, Boyd's are not very well adapted to model human behavior. In the Boyd's, the behavior is fundamentally guided by the proximity in the three-dimensional space, which is fine for fishes, for instance, that really takes into account such 3D proximity for their behavior. But as humans, we are mostly guided by our vision and less by the distance. We are going to act differently if we see something in front of us, and especially if it moves forwards, than having something beside us and moving far away of us. And one type of improvement we can add to improve the force computation is to add a dependence of the view angle. So we can model that each particle has now a limited field of view and will be able to take into account the information of the neighbors that he can see and not the one beside him. Also, and as humans, we are really good at avoiding collision. When you walk in the street, for instance, you don't only look at the distances with other people and change your trajectory based on that. You can fully pass near someone if you think that you won't collide with him. And you also tend to slightly correct your trajectory in both direction and speed without even noticing it, instead of moving straight and then suddenly changing of direction when you are too close. So it's like if, as humans, we were constantly able to evaluate the possibility of collision based on the position and velocity information we can see, and we constantly adapt our own trajectory in a way that avoids predicted collision. And this is actually the principle of velocity-based approach. In this approach, we look at pairwise agents and try to predict the risk of collision, assuming that the velocity of each agent remains constant. Then based on this information, we try to find a minimal change to apply, either in direction or in speed, to limit this risk of future collision. And to even further improve the model, we can really try to simulate what each agent is seeing in the virtual world and react accordingly, instead of actual computation of distances on a map. This is the process of the vision-based displacement model, and the idea is to render the world view by each character. Then the character tries to avoid obstacles that moves relatively toward him, which means concretely that the agent perceives an optical flow, and objects moving relatively toward us are associated to a positive divergence. So if in our vision field we have a large structure with positive divergence on our optical flow, then it means that we should adapt our path to avoid it. And finally, just a few words about existing software. Actually, there is not many software dedicated to crowd animation, but one of them is Golem, which is a software developed in a small company in France, in Rennes, and it's used in a lot of movie production, including Game of Thrones. And as you can see, it's a mix between a direct user control of individual groups, the possibility to add automatic behavior such as voids, and also inclusion of physics.